It's my great pleasure to introduce Kristin Paetzold Byhain. She's a professor and chair of design engineering at the University of Erlangen-Nuremberg. That's where she got her PhD. She was appointed professor and director of Institute for Technical Product Development at the Faculty of Aerospace Sciences at the University of German Armed Forces in Munich. Since 2021, she has held the chair of virtual product development at TU Dresden, Germany, in the Faculty of Mechanical Engineering. Her research focuses on data and information flow design, methods of advanced geometric modeling, and human behavior in design. AI methods and algorithms are increasingly being used in her research. Her work examines not only how AI can be usefully applied to development tasks, but also what transformation processes it triggers within development organization. I think the talk is very timely, given that AI is growing everywhere, and how we prepare data, what are the obstacles to it, many of the issues she will be dealing with today. Welcome, Kristin. Please, you can proceed with the lecture. Thank you.
So thank you for the invitation. Thank you for the short for the CV. Yeah, artificial intelligence in engineering design. That's really a broad topic for the first few. But I think artificial intelligence is a topic which is growing a lot at the moment. So at the moment, I'm at the design conference in Dubrovnik, and I would say 70–80% of the presentations here deal with topics around artificial intelligence. In several contexts maybe, but artificial intelligence seems to be the tool of the time, seems to be the method of the time. And I would explain, based on our research in this field, not only which benefits we have in using artificial intelligence, but also what challenges we have to consider, and in which directions we have to go further in future research to use artificial intelligence in the best manner. Okay, Sab always explained my CV a little. Let me only have a look on our research focuses. So the most important research focus for us is the data and information flow in design. Means we deal not only with processes and how to develop design processes, but also, and this seems to be most important, but also with the IT structures which are coupled to our design processes. And based on these IT structures, we use tools, we use data management systems, and so on. And this is the basis for data and information flow. The second methods for advanced geometric modeling means we use algorithmic design to create lattice structures, to create material. We use this especially for medical technology, so means we develop implants which are nearby the real situation, the real system of the human being. And here we use, for example, artificial intelligence, methods of artificial intelligence to create surrogate models to be much faster in analyzing structures we have developed. And the third part, human behavior and design, the focus here lays on how can we support the collaboration between human beings in the design process. AI here is for us interesting because with methods of AI, we can analyze, for example, talks or documents and so on, to identify critical points in design processes, or to identify points where it's necessary to communicate or to collaborate with specific colleagues. So you see, AI methods are really, really everywhere in our research. Okay, for the agenda for the next minutes, after a short motivation, I will explain some of our research results, some applications where we have used artificial intelligence, and I will show the benefits and the challenges. And it's an iterative process. So we started with data mining. Later on, we used also other methods like deep, neural networks or language models. And in our research, it never was closed or it was ended because we found new problems because we used artificial intelligence. And this way, I want to explain a little to see what is necessary to use artificial intelligence in a really concrete manner. And I close with a short conclusion. Okay, for the motivation. As everybody of you know, AI offers a significant potential for engineering design, not only in developing innovative products, but in analyzing available data and information and in supporting decisions. Means, I would say, start in the 1980s with this possibility to have CAD programs to create 2D CAD, later on 3D CAD. We started a kind of digitization of analog models we had, and based on this digitization, there was a digitalization process, and over the years we collected a lot of data, not only in design but also in analyzing design results and in verification and validation and tests and so on and so on. So we created a lot of data in the past, and now we have the possibility with this artificial intelligence to use all these data we have generated and to create from this data and from this information knowledge which support us in development processes. And yes, based on this, there are really high expectations regarding the potential of AI. But what we see, especially in practice, especially in industry, there are also a lot of a multitude of work claims that tend to hinder the effective and efficient application of AI. Means if we are not aware which boundaries we have in using AIs, then a method can be burned before we get the potential of this method. As a starting point, I try to classify AI methods, AI tools, AI algorithms, and that's really not easy because there are a lot of several classification methods. I picked out two, which you can see here. One method is oriented, or one classification is oriented on the algorithms behind. So we have artificial intelligence since, I don't know exactly, 1980, 1970. There were the first thoughts about this. There we discussed, that people discussed a lot expert systems, especially rule expert systems. We have a lot of statistical metrics we use today for data mining. And in developing AI, we create new algorithms for machine learning and in between deep learning, with which we are able to not only make data mining, but also to use this information for perception. The other kind of classification we found out was about the activities which can be supported by AI. So this is, at the one hand, perception with all these things around, for example, in image processing or language processing. The kind of learning seems to be very interesting. We see it later on. To distinguish, for example, between crowdsourcing, reinforcement learning, deep learning, and the actions which has to be supported or which can be realized by AI. For example, we can use this for expert systems, for predictive analytics, for natural language processing. Why just try to make a classification? We learned in our research there are so much methods, and it's not only necessary to have a use case where we want to have AI. We also have to think about which of all these methods and algorithms will fit in the best manner to this problem. we don't have a solution for this, but I only want to show with this slide, there are a lot of methods, and it's really helpful. At the moment, we have this hype about large language models, but there is a lot more which can be really important and really helpful for using AI in engineering design. Artificial intelligence, I explained, I will show you some examples and the things we learned from these research based on these applications. I will start with AI as a toolbox to tackle product complexity. This was our first experience. It's 6 or 7 years ago that we start with this research, and we use data mining at this time. Later on, with this reconstruction processes in reverse engineering for reconstructing geometric features, we use deep neural networks, so other category of AI for us. Then we have seen it's not only helpful to support specific singular tasks, but there are some tasks which we have to tackle, where AI may help. For example, the analysis of simulation results. We used agent-based support. We use LLMs to support collaborations. We use AI to analyze research data or to analyze research data. And our last and at the moment most important research topic is how to create a kind of workflow to bring meaning in CAD model generation. But let me start with the first point. We used, as I said, data mining to analyze product portfolios together with a company in the commercial vehicle branch. So the idea was, with the traditional approach, you can see here on the right-hand side, we have a problem. Normally we know rules how to solve this problem. This is based on expert knowledge, and based on this we create a solution. We have to analyze the solution, and if we are right, okay, that's great, then the knowledge is growing. If not, then we have to iterate. And the idea now with this data mining was, we not create the rules by expert knowledge, but we have all this data, and now we use train algorithms and to search for patterns in this data which is available. And if we found correlations, then we have to analyze these correlations. Does it fits with the problem? That's perfect. And if not, then we have to go back and think about, was it the right method? Was it the right data? And so on and so on. And as I said in the beginning, through the consistent use of IT technologies and tools, we have a large amount of data and information. And in Germany, we have a statement from companies: if the company knew what it knows, means in the data is so much more information, it's so much more knowledge. How can we make this knowledge visible? This was the reason why we started this project. And therefore, we used all these data mining approaches, classification, association analysis, cluster analysis, and so on. We had a lot of use cases from our industry partner, and we analyzed these use cases. We analyzed the data. We found out which of these algorithms will best fit to the problem. We tried several algorithms for the specific problems. We evaluate this. We compared the results. And at the end, we created small solutions like toolbox, AI-driven tools to support designer in specific tasks in engineering processes. Here in this project, specifically to analyze product portfolios and to optimize product portfolios, but this kind of toolbox and the guideline behind we can use for several problems. So the result was this guideline you see here on the right side. At first, the most important thing is to identify the use case. And believe me, in the first, it was not easy, but to identify or to to get an answer on the question, what can be a use case for AI or for data mining, because the engineers are so experienced and well known in tackling the daily tasks. They had it in mind. They had no clue in which point AI may support. But yeah, we found solutions. The next step, if we have the use case, we have to search for data which is available, in which quality is this data available, and we have to define data requirements. And based on these search for data and search for data availability, we systematically prepared the data preparation based on the algorithms we want to use. You see here 4: regression analysis, classification analysis, cluster and association analysis. Yeah, and we, as I said, we create small tools in a kind of toolbox to support specific problems. For example, the question, we create a new vehicle project, and we have to emphasize the weight or the cost of this, or how much or we have to describe the sorry, I lost the English word. Is the footprint for yeah, CO2 footprint for this, yeah, and
carbon footprint.
Thank you. The carbon footprint for this, yeah, and here we were really productive, especially in such tasks where normally the company needs a team of 6 to 8 engineers. Now, which worked 1 hour or 1 week to solve the problem, for example, to emphasize the weight. Now it needs 2 hours, and it was done by 1 engineer. And this increases the efficiency significantly. So the company was really happy about. Interesting, we then identified a lot of unknown relationship and dependencies. Yeah, and the engineers with which we work together, they get a lot of new insights in their own product portfolio. But to be honest, this was possible because these engineers with which we work together were very experienced. They have the background, they have the knowledge about cause-effect relations in creating structure and creating functionality of such a vehicle. And this was really important to get this positive feedback from the company, because we get only correlations using data mining approaches, and no meaningful action can be taken here without an understanding of causality. And this additional element to identify the causality, this was the input from the engineers with which we work together. So that's really a critical aspect. Digital technology can detect correlations at unattainably well, but evaluating and understanding, it's not possible for the AI. It has to be done by the human being. Okay, later on we used similar methods, in this case machine learning, deep neural networks also for tasks in reverse engineering. What you see here in the bottom is this reverse engineering process. We have to capture data based on, for example, CT analysis. We have to create point clouds. We have to bring these point clouds in a tessellation, in a pre-processing process, and then with this tessellation, to get to the 3D model, we have to identify the geometry features. We have to make a segmentation and a feature classification. And the first 2 steps, data capturing and pre-processing, that's completely automated. It needs not so much time, but to take this pre-processed geometry and to make the segmentation and to find out the associations and to identify and classify the features. This is where we need an expert, where we need a person with high-level expertise, and this is done mostly manual, and it needs a lot of time. And the idea was we can do this with deep neural networks, and to create this network was not the problem. The problem now was we don't have the data to train this deep neural network. We used, the first idea was there are databases for geometry, for 3D CAD models. This is the so-called ABC dataset. The problem here, in the reverse engineering process, we come from parts, we come from components which are not ideal, which don't have the ideal geometry. They have deviations because of manufacturing restrictions, because of using, because of that we have waste and such things in using the part. So the ABC dataset is not really suitable because it's not the real situation, what we want to train our network. So the challenge for us was we had this data set which only contains ideal geometry. How can we get a more realistic data set where the surfaces may be used by noising functions, someone else, get more real, show us more real the part surfaces. You see it back to the picture before. You see it, for example, in this here. There is something happen because of use of this part. Here you see typical. Can you see my cursor? Here you see typical patterns on the surface of a part. Here you see typical things between geometric features which are a result of manufacturing processes. And this is what we have to identify. This is what we have to consider when we train our deep neural network to use this for reverse engineering processes. Yeah, so we had, and that was the most important part and the most time costly part in this project, to create a database with realistic data, with enough realistic data to train our neural network. It was not too, it was also not so easy to create this deep neural network, of course, but most of the time we spent on creating the database with which we really can make this recognition of geometric primitives. So findings in using this DNN for reverse engineering, again, we had as benefit a significant increase in efficiency, but we need data. And if we don't have data, and if we don't have realistic data, all these networks or all these approaches like DNN or whatever cannot work correctly and cannot work in this precision we need to make clear decisions. And synthetic data often not represent realistic situations, and it needs a lot of brain to create synthetic data which is really usable or useful in this specific contexts. So it needs methods to create and manipulate realistic and reliable data. Okay, and but in between these processes, large language models start to be to get more importance. So and that was definitely a game changer in using AI. Our first experiences with this were to use large language models in enabling as an enabler to support collaboration. This was also a big project together with a vehicle company in Germany. And the idea was in every project, and when they start a new project to create a car or to design a car, then they build up a first CAD model. And in this first CAD model, they explain the interfaces between the specific parts in the car. And based on these parts of the car, the development task will be distributed to the several organization units, to the several teams to develop. So, and now the question was, if there was make a change in the CAD model, then you have to inform a lot of people because this change may be interesting also for other development teams, also for other people in the for other functionalities, for requirements, for changing requirements, and they create issues because of changes anywhere in the CAD model. So, and here the idea was, can we use large language models to support this collaboration? At first, it was, to be honest, one problem we learned with this both projects before. We don't have the problem with the number of data. We have the problem with the variant data. So we have data not only in the same kind of data set. We have data from CAD, we have data from simulations, we have data from tests, and so on and so on. And the problem is to bring these data together. Yeah. And large language models are not able to do. I can make a search with large language models in text-driven or textual documents, but not in CAD models, for example. So how can we, overcome this gap at least? So, and the idea was, we can build up a knowledge graph based on our CAD model, on our first CAD model. And in this knowledge graph, we can connect the design parameters with design features, with the users, with the design teams, with several issues which are necessary to mature the project, and so on and so on. We create this knowledge graph. You see part of this knowledge graph in the picture. And now, how can we organize the information management based on this knowledge graph? So, and here we use large language models to analyze the data and the information flow in the large language model. We not directly go to the data. We only have a look for which data is in which interface necessary, can be an input, must be an output, to ensure that everyone has enough data and the right data at the right moment to make decisions. And therefore, these LLMs were really, really helpful. And they again, not only the efficiency was high, the quality of the collaboration grows extensively. Okay, so the benefit, increase in efficiency, yes. Critical aspects, sorry. Sorry. Was not the right direction. In this direction we have to go. Okay, large language models. We can overcome this gap that we have a lot of data from several data sources and with several characteristics. And in the second step, also with a commercial vehicle company, they asked us, can we support via large language models the analysis of results of simulations? So we have a simulation workbench, and this process, pre-processing from having a CAD model, bring in the load cases, bring in the material, create the finite element mesh, and append the loads and constraints, solve. This is more or less automated, yeah. But when we get the results for all these load cases, we have Excel files with the data. We have UML files with more information. We have all this information from the load bases, from the material database, and so on and so on. And the designer, the engineer now has to switch between several tools, between several pictures. Sometimes you have pictures, sometimes you have the CAD model. There's so much information, and how can we support the engineer in switching between these tools for gathering the information to make a clear decision about the component or the specific simulation or the specific component is okay or is not okay. And as I said, heterogeneous data must be examined, compared, and analyzed. So, and here we use the so-called compound LLM for post-process this post-processing process. We had this links the tools using an agent-based approach for information retrievals, and the compound LLM acts as a layer between the engineer and the simulation data. Material databases, other AI models for data analysis and calculation tools are also integrated in this construct. So we have here the situation, there will be create a result based on non-deterministic approaches, AI, as well as deterministic approaches. So we have rules behind. And now the question was, the decision the designer has to make is based on a mix of deterministic and non-deterministic analysis. And with the experiences the designer have today, it's not it's possible to make this decision. But the decision remains that every designer has a specific experience, a specific background, and that must be addressed by we said, okay, the engineer has to get the information, which of the data is from a non-deterministic approach, which of the data is from a deterministic approach, that he can evaluate the results and the results quality. And we try to do this via a human-machine interface, which is specifically shows where are uncertainties and what does these uncertainties may mean for interpreting these results. This leads us to a specific problem. Now we have to validate this method. Yeah, before the company will use this method, it must be validated. And we have seen to make the validation for the deterministic part of this method was not a problem. We can use classical approaches, and it was okay, it was fine. But what do we do with this non-deterministic part? So here we spend a lot of time to create or to find out new novel validation approaches. You see here in this pyramid or kind of pyramid that we not only have to make something about the correctness. We have also to say something about model capability and reliability. Not only the functional adequacy has to be analyzed, but also additional value, which has been created for the engineer. And it's not only the traceability, it's also the credibility we have to validate to get to ensure the transparency of the results of this method. And we spend a lot of time in creating this approach, of course, but also in validating this approach. And here we must say that is a first try, and I'm sure here we need much more research to validate methods based on non-deterministic solutions. Okay, so what we learned from this project, again, a significant increase in efficiency is especially through the collaboration between AI and human intelligence, means the designer. And we have a consistent use of available information. That's important for us. It's not only to have a look for one database. Now we have much more, now we can use much more information and data. But the critical aspect was the cognitive work, now previously reserved for humans, was now being taken over by technologies, algorithms. And how does this affect the development of skills, experiences of the designer? How does this affect our own integrity? Not at the moment. At the moment, our engineers are experienced enough to validate the results. But what is in 5-7 years when designers not have this experience like the designers have today? And the third critical point was how to validate these AI-based tools. And what we learned here, do we need a change of the perspective in using AI for engineering design tasks? Why? Normally we start in a use case, we make this data analysis, we build the models, process these models, and then we can use these models. But we learned in identifying the use cases, we identify requirements for the data, and we see normally, or we have seen in the past normally, there's not enough data, not the right data, and not the right quality of the data. And we start to collect data. We start based on the requirements. But this leads to a change in the use cases. This leads to variations in the use cases, and then we start the cycle again. So it seems to be not so efficient. And the second thing is, with this AI, we neglect at the moment engineering semantics in engineering in data analysis. So we make this data analysis based on informatics, based on computer science requirements from computer sciences, but we have strong engineering semantic behind all these processes. I have to make a mesh for a finite element analysis, and based on this mesh, I get a specific quality. And based on this mesh, I have to have a look on specific points in my part in the analysis of the results. And here I think we are weak, and we have to think about how to deal with this. And the second thing is physicality and function is neglected, at least in using AI. We only concentrate on the data, but we don't consider at the moment enough the physics behind these data. So this leads, and this we learned in this last project, what I want to explain here shortly, or I see I'm out of time. Automated generation of geometric models. At the moment, here in Dubrovnik, on the design conferences, we had 2 keynotes which deals with automated geometric modeling in 3D CAD. Yeah, and it's beautiful what they do, but in a 3D CAD model, you not only have this geometric information, there's information about functionality, there's information for manufacturing, and so on, and so on. And we create today such CAD models, but without content, and they are useless for us in the engineering design process. The complexity of these models was increased in the past perfectly, but there's no context information in these models. But if we create a 3D CAD model, we need this model for the whole product development process as well as for the production process. And if we don't have this information, it's useless to create geometric models via AI. And this is where we are working on at the moment. It's not ready now, it's only an idea. How can we combine form and function in automated creation of CAD models? And the principal idea is sketched here. We have, similar to topology optimization, a kind of load case we have given. We have the loads, we have boundaries, and now within the CID engineer can make a requirements text, can make the requirements rendering, and based on this, an LLM, a kind of LLM, creates a parametric CID model. And this parametric CID model, now we have to analyze, we have to evaluate, and for this evaluation, we deal with specific metrics and specific methods to say something about the physical correctness of this model. So this is combined with a kind of finite element method. I'm not an expert of this, is one of my PhDs, but he coupled surrogate models and FE analysis with this LLM model he created, and try to bring in more information in this CAD model. We are here on the beginning, but this is necessary. This is what we have to do. Otherwise, we create nice things with LLMs or with this generative AI, but it's not worthwhile for us in the development process. Okay. And the second thing, you know this, I make this presentation at the Design Theory Conference in January. Now we have a collaboration between parts of human being and AI, and these human tasks in these collaborations, the human can anticipate dynamic changes. He can deal with uncertainty. He can evaluate AI results in the context of a current situation based on sound expertise and knowledge. This will change because if I only use AI, then I don't have the possibility to make experience, to learn. How do we do this? Yeah, how do we deal with this? The humans have to understand the decisions made by AI, and the question is, how can we support this? How can we do this? We discussed a little this so-called Polanyi paradoxon. For AI, it's impossible to codify implicit human knowledge. This means when humans receive results from AI, they cannot understand or interpret the process by which the AI generated this input. And also the AI underlying data analysis and evaluation are known. They are non-deterministic, and so uncertainties always remain. It lays on the process. This is discussed in literature as the AI as a black box. And to challenge this, we have to give the possibility to make testing and experimentation with the results. That leads us to experiences. Or maybe that can be an approach to how to create the human-machine interface that the human being is more able to understand the results from the AI. Okay, based on this, we defined requirements for human-machine interfaces. So a highly automated interface leads to excessive dependence on the users. It dequalificates the user, but an extensively detailed interface leads to a user overload, and it reduced efficiency. What is the right mixture in between this field we have here? So the design of the human-machine interface influences workload determined by necessary specialist knowledge and experiences you have. But this human-machine interface must support the formation of mental models for the engineer. Only then he is able to interpret the results from he get from the AI. And in such a way, the transparency is guaranteed. Maybe. Question is how to do this and how to create such a human-machine interface. But at least here I would start. I would stop. Yeah, because this is another very big topic where we can discuss about this collaboration between human intelligence and artificial intelligence. What I want to show with this presentation, AI is really powerful, and we, especially in our institute, make a lot of very positive experiences in using AI to support efficiently a designer in the daily tasks in the development. But there are also a lot of things we have to consider, and not only considering we need the right requirements in using AI, there's also a lot of need for research to solve or to tackle these problems or to tackle these critical aspects as I explained here. What you see in this picture on the left-hand side is what I tried to explain with this CAD model. Yeah, it's not on. Our first experiences was to use AI like a data scientist. Yeah, we have these use cases, we have the structured data, we create toolboxes, and we have a process how to use these tools in this toolbox. With this large language models as a game changer, with these transformer models, we can also address prescriptive and generative use cases. We can do this for unstructured data, really great. And we also here have a kind of toolbox with which we can work, and the manner how to work with this has changed, yeah, from a data scientist to an AI engineer. But our opinion is this is not the end. Yeah, at the moment we use all these interesting methods without engineering semantic, and this must be the next step. How can we include this engineering semantic? Yeah, that's all. Thank you for attention.
Thank you very much, Kristin. We will open it up for questions, and I think you have raised some very, very interesting points. Is the question of how do you embed AI and knowledge structures in such a way we don't lose the skill base of the engineer. And these systems need to not only provide ways of creating solution, but also identifying how one can explain the solution itself using appropriate knowledge structures. I think that, as you correctly pointed out, has an important obstacle that needs to be overcome. I think there are ways, I think I've talked to you a little bit about it, as to how we can address those things by bringing additional mathematics of relationships using something like category theory. So we can talk about that later, but I think there is a bridge that needs to be built. And I think we have to be careful, as you pointed out. Making AI models black boxes is a dangerous way to go. And thank you for raising those issues, because often we apply AI without thinking as to what is the consequence of it in the long run for the skill base of the people who will be future engineers. Thank you for that point, because I think it's a very important point that often people forget when they apply these methods. So that is my comment, and I'll let other people ask questions along these lines.
Yeah, thank you for the comment. That's my pain, what I have in using AI. Yeah, today we can interpret these results because we have these experiences, but what is in the future? And here we have a research together with, we can't do this as engineers alone. So we have research together with social scientists, for example, because they are able to explain these processes much better than me. So yeah, we will see. But yeah, you're right. That's the most important point.
Anybody else? Yeah, go ahead.
Yeah. So yeah. I have two questions, but the first one is, suppose a company is involved in manufacturing car wheels, right? And suppose there is a requirement to come up with a new wheel design for a particular new vehicle. And the company may have a knowledge base of having designed similar wheels for a variety of automobiles, right? Now, where do you see this AI intervention coming in? Is it in exploring and coming up with a new CAD model for the new vehicle, or taking it to the next two levels of actually doing the physics and FEM validations or the fluid dynamics validations? So is it cutting across all these stages, or is it in the early stage of exploring what the form of this new wheel should be?
I think here we have a little to distinguish. If you only want to have the new form of the wheel, these gun models, for example, are really, really strong and really, really good. But you can create a design, but then you have to calculate and you have to make all these mechanical simulations, fluid simulations, and so on. You can do this as well with AI approaches. For example, I know colleagues which they use so-called surrogate models to make these simulations, these time-consuming simulations in parallel and to be more efficient. It's a question of boundary, I would say. Yeah, if you only want to have the design, that's one point. If you want to have the calculated design, then you have to include more data, then you have to think in another way how to connect maybe AI methods, AI algorithms to get a result. It's possible today, I'm sure. If you want to know what does it mean if to have a new wheel on the car with all these interfaces, and how which person do I have to inform because there are changing in the requirements, then this is another thing. It's not the same AI. You need another construct of methods, tools of AI to solve or to support these problems. There is no one AI fits all. That's the problem sometimes.
Yeah. So, the other challenge is you are talking about working with the knowledge base of a company, which is a proprietary knowledge base, right?
Yeah.
So how much can you leverage some of the available AI tools in doing this? Or you'll have to do grounds up for each institution, or how is it?
That's a critical point. Hopefully I understand your question right. We only can do this research because we have these industrial partners, because they have the data. We try to generalize our approaches, and we discuss these approaches with other industry partners, for example, but it's normally not possible to take the solution, for example, this agent-based support for simulation analysis from one company and put it into the other company. That's not possible because the IT structures are completely different. And this we have to consider, as well as the process is different. Yeah, the experiences are different. And this is what we have to consider in building up such an agent-based construct, in building up such a compound LLM.
Yeah. Okay. My third question is, you mentioned about the knowledge graphs. So, and also the hidden side of AI. Now, what really happens to the organization's knowledge base when you start intervening or adding more AI into that?
Good question. I don't know.
Right? I'm more looking from the CK theory perspective. What happens to that knowledge base and what are the implications of that?
Yeah. So I think it starts a transformation process, to be honest. Yeah. If I use this knowledge graph, for example, this to support the collaboration, yeah, then the communication ways change. how they communicate, this changes, yeah, and this leads to changes in which data is necessary, is available, and which data quality is necessary, and so on. So I'm sure it changes the process. It changes not the process themselves, but the kind of communication between involved stakeholder here. And this is a transformation process we have to consider. I don't know how and in which direction this goes. That must be research for the future.
Thank you.
Any other questions from the audience? If there is none, I have a question. I think you have pointed to something which I think is very important. How do we capture and encode the knowledge in such a way that it is available to the user to examine inside these boxes, what it is doing, why it is doing what it is doing? Do you have ways of capturing the conceptual structures and at the same time the specifics in the knowledge base for a particular company or a particular context? That still seems to be a very open question we need to address in the future. And we need to find, I think, new ways of encoding, and also in the human machine interaction you pointed out, how do we actually also extract the knowledge from the user in a particular context to augment the knowledge base itself? I think that question still remains open. That is where both social scientists and cognitive scientists become very important for us to see how the machine and the human operate as a collective. I think that is something we often forget, because language is at the heart of everything. And if you don't have the right language, then you don't give the right answer. And there is a whole set of things that we need to do. I think it is very, very important. I think you have raised very important questions that anyone doing AI in engineering have to pay attention to. I think this is really wonderful in the way you have described this whole process and the larger problem, not just the problem of adding an AI somewhere. It's beyond that. And I think that's a very interesting and important point that is often missed. So
Definitely,
really, thank you very much for exposing those things in a very clear way in this lecture. Thank you. And I think, anyway, I will talk to you later about, I have some ideas on this and how we could proceed with that. Maybe we can talk about it at some other point.
Perfect.
Thank you. Thank you, Kristin.
I thank you for getting this possibility.
Oh, thank you so much for giving this lecture, a very important lecture from our perspective, especially as AI is used, it's becoming profuse, and the importance between collaboration between industry and academia here becomes very critical in understanding expertise, understanding transfer of knowledge from one generation to another, which I tend to think of as creating and managing collective memory of multiple engineers. I think it's an important aspect which we need to pay attention to, because we can't follow the computer scientists just by themselves. Then we'll get lost again. I think it is something that needs to be paid attention to very carefully. And I think that point is very well taken. Thank you very much. Anybody in the audience, any questions? Oh, okay, you got a note saying thank you for the informative talk. Yeah. Anyway, thank you very much for this. We don't keep you long. You're in a conference and you probably have some things in the evening, afternoon for you sessions, which I don't want you to miss. And I would like to look at the proceedings of the design conference you are in to see how people are looking at AI. I think that would be very interesting to see.
It would be, I'm sure. There's so much input in this conference.
Yeah. Sunil, anything else, or should we?
We are fine. Thank you, Kristin, for the wonderful presentation. There are a lot of questions that I've got, so but anyway, we'll keep in touch. Yeah.
Well, you can send her a mail.
Keep in touch. Yeah. Okay.
Thank you.
Okay.
Thank you very much.
Bye.
Have a good afternoon and evening.
Thank you.
And we'll see you sometime soon.
See you. Bye.
Bye. Thanks.